Thank you so much, everyone, for being here today and joining us for the inaugural Eyes Off Data Summit 2023. I'm Ali Rizvi. Yeah, let's kick it off. Did not have that planned. I'm Ali Rizvi. I'm head of community at Oblivious. I will be introducing all the speakers today and mispronouncing their names. And today, we have curated an excellent panel of experts for you. And the theme for today is understanding the state of the art of pets. Pets have come a very long way since we started. And now they're ready for industrial scale deployments. We'll be seeing today where the cutting edge is. Tomorrow, we'll be getting our hands dirty and understanding through various workshops what we can do to deploy them practically. And we have various breaks throughout the day, so hopefully you can have fantastic conversations and walk away with a deep understanding of how you can deploy privacy-enhancing technologies in your context. Now I'm going to invite Rob. Already did that. Now I'm going to invite Jack, who is the CTO of Oblivious, to talk about creating a common language for data privacy.
I took the steps. I thought that would be a slightly better strategy as the first person up. So a common language for privacy. That sounds very much like we might have some overarching framework or way of tying everything together, and that is not what this talk is about at all. We realized that today we've been trying to bring together people from different communities. So there's like lawyers and regulators and data scientists and software architects and academics and people who build pets, etc. And we thought it would be a good idea to just start off the day with just running through basically some of the kind of jargon. So at least people have the right words, so when they meet for a coffee break or a glass of wine, there's some kind of mutual language to be able to talk and reason about these things. So the kind of overarching theme that we're going for is that we live in the era of data, and yet most of the world's most impactful data resides in silos across one or more organizations. It could be government, it could be private sector, it could be at a university in a research group. And the idea is, how can we use these new technologies called privacy-enhancing technologies in order to unlock that and be able to create real value from it? So we'll start off just with two kind of toy examples as just kind of potential challenges that you would see today. And we'll just ask ourselves, what's the issues with this today? And then maybe, what could we do better in the future? And maybe how privacy-enhancing technologies might enable that. So the first example, just as a straw man here, is imagine like a taxi hailing service, right? Pick your favorite. We can make up an imaginary one. And assume there's a data scientist in it. And like what your job as a data scientist is most of the time is looking at data and then pulling useful information to support other teams, right? So it could be you're trying to support the sales and marketing team to better, market your taxi hailing app or something like that. But at the flip side, you shouldn't be able to tell that your buddy is like in a taxi now going across town, right? So there should be a balance that you can't kind of spy on people or have God view, but at the same time, you can do your job. So how do people do this today? Well, very often, you just get direct access to the data, and that's maybe not the best governance in the world, but people try, right? So one approach to this is masking what's considered to be PII, like personally identifiable information. So this could be maybe stripping out email addresses or like hiding names, just crossing them out, XXX or something, maybe mobile numbers, etc. You could completely try to de-anonymize it, but maybe the data is not that useful in the end. And even still, if there's any way to like link together maybe a person's set of trips or something, you could reconstruct where someone is. So if our friend Bob does yoga in Smithfield every Thursday at a certain time, if you start looking them up, maybe you find the identifier for that person. And even if there wasn't an identifier, maybe you can just figure out if they skipped yoga last week because no one took that taxi route. A lot of people are now doing probabilistic masking as well, using machine learning and AI, but that means they're kind of guessing and hoping for the best when they try to strip off this data. Another way of doing it is just giving people access to aggregates. So instead of telling people about individual records, maybe you just group them together, and maybe it's harder for them to directly learn about individuals. But it turns out, once again, this is not the strictest set of rules in order to hide information about people, because depending on the aggregates and how you bring them together, you can actually learn a lot more than maybe you're allowed to or intended to. Another challenge here is that often you don't know what aggregates the data scientist is going to need ahead of time. So it's a little bit hard to even put that in place. OK, let's go for another example. Example number 2, we have a ton of law firms across the river here. So imagine you're a lawyer in a law firm, and you have a bunch of international colleagues who give you documents, and they're in different languages, and you need them to be translated so you can, I don't know, do your job. So it would be nice if we could use, I don't know, an online translation service or something. But what you'll find is that, typically speaking, they don't do that, because otherwise you're sending potentially confidential data to translation company X, right, to one or another. So when you're using a third party, how does it work today? Realistically, you kind of have to trust them. There's certifications like the ISO 2700 series or SOC 2 or something, and there's privacy policies, but it's very hard to know if anyone's broken this unless there's like a data leak or you're going to sue them. And you don't really want to be going down either of those two paths. So just the sheer trust relationship between organizations can limit companies to offer services to one another and hopefully build tools together or do commerce together. So that's really the problem. If you're a data scientist, getting direct access to a data set, maybe multiple data sets. If you're on a computer talking to a SaaS tool, at the moment, we can secure the communication. When I say at the moment, day-to-day at the moment, so like what you currently see. You secure the communication from your computer to the server you're talking to, but you don't really have any guarantee about what's happening at the other end. Data scientists are obviously blocked from doing their jobs sometimes. Businesses have limited data analysis that they can really leverage. There can be compliance challenges. So if you want to work with another group and you've SOC 2, there's like a network effect, so it can limit who you can work with or how you go about things. We've got some regulators with us today as well to talk about regulations, etc. There can be simply a lack of trust and transparency, and there's no really kind of reliable way under those guises to handle sensitive data. Especially, I think everyone's talked about LLMs and hot AI topics, etc. And while these can be super useful, I think we've even seen in the press organizations that sent sensitive like IP to them, etc. And there's a ton of pain points that have emerged from that. So these great breakthroughs can also create challenges around data sharing. So what an ideal solution would look like, at least as the pets community, I hope I'm representing us all relatively well, is to say, it would be great if we could enforce a transparent trust model. Where do each of the inputs come from? Who receives outputs and what could they do with that? And what processing is allowed during that interaction, essentially. And there's different guises of trying to give an overview of the field, but probably the easiest is to think of it in terms of input and output privacy. So any server or computer program that you're using or when you're interacting with maybe colleagues or consultants, there's an input phase where you're sending information or data to the counterparty. And ideally, during that, you want to know that the data is used for its intended purpose, it's kept secure, it's only used, it's protected from the eyes, maybe of their engineers or support engineers, etc., during that interaction. And there's output privacy, which is like when you get an answer from the questions you've asked, how do you ensure that those answers can't be used to reverse engineer the original inputs? So you've got input privacy, protecting the inputs coming in, and output privacy, ensuring that the outputs don't back reveal the original inputs. The ideal solution would try to integrate data from diverse data sources, so you have greater data accessibility. It guarantees that data usage adheres strictly to its intended purposes. And the disseminated outputs prevent reverse engineering of the sensitive information. OK. I hope that gives a little bit of an umbrella term for pets. Now we'll do a quick run-through of the actual technologies that are kind of currently available, either from academia or there's solutions on the market for them, or there's different tools that are being created by industry. And we'll just do a quick run through. We're not going to go into any depth, but we're just going to tell you a little bit about how they work, slight pros, and kind of the cons as well, right? So nothing is perfect, and just understanding how these Lego blocks come together allow you to maybe reason or have a debate with the person next to you over a coffee. So we'll start off with the input privacy, and we'll start off with kind of cryptographic-based input privacy methods. So we have, for example, the Infair crowd are in the room with us, and they really work in the MPC space, along with a number of others. And these use basically cryptography in order to encrypt data, but in such a way that you can still apply certain functionalities to the data. So you can still add two encrypted data points together, for example, and the result is also encrypted. So in doing that, you don't directly see the intermediate values or any of the inputs through that computation. When people say we process encrypted data, like it's always encrypted or something like that, that's only technically correct if you use one of these schemes. But there are many ways that you can do this. So one is if you have multiple parties, like maybe banks or something like that, and there's 5 of them, and you're all sharing information together, and it's all encrypted according to a strict scheme, and people are essentially sending messages back and forth to each other and combining or mixing that data together. There's outsourced MPC. So if there's a trusted consortium, let's say there's 3 government institutes, and they're not going to collude with one another, you can send them kind of shares of your information to different ones, and again, they'll do those interactions on your behalf, so you don't need to do the heavy computation on your device. There's also things like homomorphic encryption. So we have the Samsung team here and others who work very much on HE, and this is when there's just 2 parties involved. So you encrypt your data, you send it up, it's processed, you get it back. However, there are advantages, which is you never centralize the trust, you never decrypt the data, etc. But that's a very compelling reason why you might want to look into these. And it's also a very active research community at the moment. So I think there's lots of universities trying to push the bar forward. And I think as we talk tomorrow, there's a bit on standards. There's some efforts working towards standards in the homomorphic encryption and multi-party computation space. Some of the challenges, and again, because there's so many types of schemes here, this is a bit of a catch-all, but typically they're quite computationally expensive. So sometimes things will take like tens of thousands of times slower than just regular processing. So things that are feasible on a normal computer are infeasible in certain schemes. Sometimes it can be heavy in terms of bandwidth. You're sending lots of messages back and forth. And there's no, when you talk to a CISO, usually they want things to be like FIPS certified. But these, yes, it's encryption, but because these schemes are not the kind of standard encryption mechanisms that people use, they fall outside of that. And so even for security teams, sometimes it can be very hard to distill trust. And obviously, in multi-party cases, collusion between people and collaboration can break and unlock that originally encrypted sensitive data. So the first input, you encrypt it, you manipulate encrypted data. Usually you can apply like a polynomial function, or you can do like additions, multiplications, greater than or equal to, etc. That's the kind of world of the encrypted methods. Another approach to this is secure enclaves. A synonym for it will be confidential compute or trusted execution environment. And how these work is they have extremely isolated, usually hardware, that limit the inputs and outputs from the kind of parent device. And what they do is they take a snapshot by hashing all the software that's running inside as it gets booted up, and the actual underlying infrastructure provider, a cloud or a chip manufacturer ideally, digitally signs a document saying this is what's running inside. So you can basically use the infrastructure providers to give you a level of trust in how your data is being processed and how it's being secured. Benefits to this is you can just run software in it, right? So it doesn't matter if you're running C or Rust or Python or Java. You can run this inside the VMs, which ultimately run inside of the enclaves, which means you don't have to rebuild everything from scratch, which is can be a costly task. And like your communication channels in and out can all be, for example, FIPS certified, and they can follow conventions like TLS and all of the nice parts of this, how hashing is done, etc. Some of the challenges is obviously once inside of the enclave, you do decrypt the values, and that's the benefit. So you can decrypt them and then process whatever software you want to actually use the data. So it's a benefit, but if you're super paranoid and you never want anything to be decrypted in any regime at all, it's just a trade-off that you have to take. If you have like a software that you would like to actually run, packages and frameworks already there, this is kind of the clear way to go. If you want to build everything from the ground up on those low-level kind of cryptographic schemes, the former is the way to go, essentially. Then we move on to output privacy. So you get data out. How do you make sure no one can reverse engineer the original inputs? And what's been around for like 100-odd years are census bureaus, right? And there are many of them, not just census bureaus, but economics groups, et cetera, healthcare, giving statistics to the general public. And how they keep your data private is typically from statistical disclosure controls. So they've just been used for a very long period of time. Usually there's teams in the organization that bin together the data. They make sure that data is aggregated. Some noise might be applied. There's things like data swamping, et cetera. And they've just been around for a very long time. The advantage is that things that have been around for a long time kind of have been battle tested, so there's a lot of trust, and they're often just the things that are used in practice a lot today. But some of the challenges are around how you actually implement these, and also if you're giving multiple different types of releases and, let's say, reports, et cetera, what's the knock-on effect of sharing different statistics over a period of time? So it's hard to kind of combine how much information you've really released over an extended period. That was the previous one. So differential privacy is the kind of alternative to that, which was invented, I think, 2006, I believe, so about 17-odd years ago. And its approach is it follows one mathematical formula. It'll be discussed later tomorrow, I believe. But essentially, it's adding noise to outputs, and just enough noise that it hides the influence of any one contributor to a data set, or any one entity. And so all of this is highly calibrated, and just the beauty of the mathematical scheme is that you can track from one query or one machine learning model or one report that you've published to the next, to the next, to the next, tracking how much, quote-unquote, privacy has been lost throughout all of them. Mathematical guarantees are obviously a benefit, and it allows you to track the privacy over multiple queries. Again, some of the challenges. Track the privacy. So this gives you a number of how much, quote-unquote, privacy budget was released. So what is the level before you think something is safe? Not always clear. There's also a limited number of standards available currently too. But there is more and more frameworks coming out, and I think there is efforts towards standardization. So differential privacy, because of this nice mathematical nature, can be just applied in many different schemes. So the following output privacy techniques are really just differential privacy methods in different structures, really. So just to recap again, we've got the input privacies, cryptographic or isolated environment through trusted execution environments, confidential computer, secure enclaves. And then you've got the output privacy, which is the status quo that's been going on for like 100-odd years, statistical data disclosure controls, and differential privacy, which is the newer kid on the block, but is massively growing in popularity and was even used in the US Census in 2020. So it's large organizations are kind of seriously using it. Now, one thing you'll hear a lot, because it's very non-invasive, is, well, what if in giving someone access to the raw, sensitive data, what if we just created fake data that look like the real data that maybe a data scientist can work with, and we'll give them some results, but it won't contain any of the original individuals, et cetera. And this is called synthetic data. So how it works, essentially, is there's either statistical models or machine learning models that try to figure out what the distribution of the data is. So how do you create fake data so it looks like the real thing? And then it uses that model to just take samples and create dummy data. You don't have to change any of your tools when you're using synthetic data, so that's a huge advantage. But one of the main disadvantages here is there's a guessing part. So whenever you apply a statistical model or a machine learning model, you're making assumptions about the data. So you make model assumptions. So let's imagine there's 3 bumps you can fit to data, but imagine the data actually has 4. and the fourth bump is an entire community of your society. So if you fit those 3 bumps, you might do a great job, but maybe you've just lost all of the information about an important stakeholder group. Federated learning is different again, but again, typically leverages that concept of differential privacy or similar. And this is really being pushed by like the companies who do a lot of stuff with mobile phones. I think that's like where you'll see it a lot, like apps and operating systems for mobile phones. So the setup here is you just have lots and lots of people with devices, or maybe lots of institutes or whatnot, and they want to locally process their data and then send something back to a centralized server where basically, before it's been sent, they've cleaned it up, maybe they've applied differential privacy, and the thing going back can't reverse engineer the original information at the device level. So, for example, if you're on your phone and you've got predictive text and it's guessing the next word, they want to continuously improve that, for sure, but they also don't want to read all of your text messages, right? I mean, they're trying to balance these things. So they're trying to get estimates of how well they're performing over a period of time, but they don't want to be spying on you. That's how federated learning is trying to balance these things. But again, it's another scheme that can leverage differential privacy, but now in a very distributed way in order to get some insights. Advantages, obviously, locally processed, and you can have assurance that only non-sensitive information is leaving your device. And some of the challenges that if it's not using differential privacy or something similar, you actually have no guarantee of what's going on. Very similar to synthetic data. If there's not differential privacy in there, it's very hard to actually say that what you're doing is safe. So I just listed off a bunch of technologies. I'm not expecting anyone to be an expert in any of these. But input privacies help you when you're sending data to somewhere. You want to make sure it's only used for its intended purpose and no eyes are on that data. That's basically it in a nutshell. 2 branches, cryptographic or based on hardware, essentially. Output privacy, you're releasing something to someone now. How do you make sure they can't reverse engineer the original inputs? You can do the manual work that like census bureaus have been doing for a century or so, or you can do the more kind of modern automatic version by applying calibrated noise called differential privacy. And then as seen in the last 2 schemes, you can kind of combine these together in different ways so they're more fit or appropriate for your particular use case, either through federated learning or by synthetic data. So hopefully, this is a toolbox where there's very different people in the room who work on different types of technologies, but hopefully, as a group, PETS will give us some ability to use the world's most sensitive data to actually make tangible changes in society. Great. So with that, I will leave you to the next speaker.
Thank you, Jack. And hopefully now we all have a common language, and there will be a quick quiz after this, so hope you took notes.